Good morning. My name is Chichilnisky, and I'm going to be talking to you today about our efforts to develop novel technological treatments for incurable blindness. Now, obviously, blind people have capacity to use assistive technologies of various kinds, including the wonderful stuff that we heard about this morning, or including older assistive technologies, such as shown in this slide, to navigate their world and perform basic pseudo-visual functions. On the other hand, we might ask the question, could we possibly restore vision to people who have truly lost their visual sensation at the level that we normally experience vision, of high-resolution images, navigating rapidly changing environments all the time, appreciating new faces and facial expressions, and even appreciating beauty? Now, many forms of blindness are brought about by degeneration in the retina. As a reminder for you, because maybe it's been a while for some of you, the retina is a sheet of neural tissue at the rear of the eye, and it performs three major functions to initiate vision. First, it captures the light and transforms the light into electrical signals. Second, it substantially processes those electrical signals. And then finally, it sends the electrical signals as nerve impulses down long optic nerve fibers to the brain. Now, in many forms of vision loss, what happens is one layer of the retina, the so-called photoreceptor cells at the rear, which capture the light and transform it into electrical signals, are lost for a variety of reasons. However, many of the other cells in the retinal circuitry remain, opening up the possibility of a technological intervention, such as the one illustrated schematically here, involving first a camera that captures the visual image, circuitry that processes the visual image in a way that perhaps mimics retinal circuitry, and finally, electrodes that electrically stimulate the remaining retinal neurons to deliver artificial signals to the brain. If we do this right, perhaps we can create signals in the neurons sending information to the brain that mimic naturalistic visual experience. Now, this is called a retinal prosthesis, and it's certainly not our idea. People have worked on this kind of technology for decades, and in fact, there are several kinds of retinal prosthesis now available for use today. The spectacular news is that actually these devices can deliver some kind of visual sensation. People who have been profoundly blind for decades report seeing flashes of light and even being able to perform simple tasks with those flashes. On the other hand, it's nothing like the normal richness of our visual experience. And in fact, these devices are typically not appreciated as even as useful as a cane or a guide dog or perhaps as the vest that you heard about today. Now, why is that? And is there a possibility of restoring the richness of visual function that we simply can't do with other devices? Well, what I'm going to tell you about today is that there's one aspect of the neuroscience of vision that I think tells us the answer about where we need to go. And the key aspect is illustrated schematically in this slide. There are, in fact, many different types of retinal neurons on the output of the retina that send visual information to the brain in their spatiotemporal patterns of electrical activity. And the patterns of electrical activity in the different cell types are very distinct from one another and are transmitted to different targets in the brain. It's a rich, complex neural code, if you will, sending the information from the retina to the brain. The problem is that these different retinal ganglion cell types are not laid out neatly and separately from one another, as shown in this slide. In fact, they're all mixed up with one another on the surface of the retina. So if you introduce a grid of electrodes and simply try to stimulate in a way that replicates the pixel pattern on the image, you can't create these complex patterns of activity that are normally transmitted to various targets in the brain. So what we'd like to be able to do is to recreate those patterns of activity. You can think of this perhaps as an orchestra, and you're trying to conduct this orchestra to play a particular symphony. Every instrument in this orchestra has its own particular score, and it's the mixture of all those different and distinct scores that creates the actual music you're trying to produce. Stimulating the retina, as all current devices do, in a way that doesn't respect the cell type organization, is somewhat like conducting an orchestra without paying attention to which instrument is supposed to play which score. You're not going to produce the music that way. You might produce something a little bit closer to noise. So can we do that kind of thing? Well, we can do that in a substantial manner in the laboratory today using experiments illustrated schematically here, where we take very small, high-density electrode arrays and place them up close against the retinal surface. We do with electrodes that are about 10 micrometers in diameter, comparable to the size and spacing of the cells that are there. With these devices, we perform three major operations. First, we record the electrical activity of the individual cells and separate them out from one another to figure out where the cells are, each one, and what different cell types are located where in this particular retina. Second, we electrically stimulate and record in order to figure out what kinds of pattern of stimulation are required to activate this cell or that cell or that cell or that cell, and so on. And finally, we put all this information together, and when an incoming visual scene appears, figure out how to optimally stimulate this collection of cells across the region of retina with this fine-grained electrode array to reproduce the normal, realistic, cell type-specific patterns of activity. Now, the problem, of course, is that you have to do this not a few cells at a time, but at a much larger scale than that. A slightly larger scale is shown here in the retina with a bunch of different ganglion cells of different types interspersed in the retinal circuitry with their axons running over the surface of the retina as they do. So with a large-scale electrode array, we go in and electrically stimulate and record, as I just told you. But the issues are figuring out all the different cells, all the different cell types, and stimulating without activating the axons and so on. So it's a complex pattern of activity. Long story short, we can do this pretty well, quite well, actually, in the laboratory environment. And so the big challenge for the future is figuring out how we can translate those observations in the laboratory to developing devices that we can implant eventually in humans. And we have a project here at Stanford called the Stanford Artificial Retina Project, which involves myself as well as collaborators in electrical engineering, computer science, material science, and other groups putting together the artificial retina based on this kind of work. And that's our goal for the future, is to produce that device, and we're hard at work on that. Now, what I've told you about is our focus on treating incurable blindness, and I want to just end in the last couple slides by pointing out other applications of this kind of approach. So many types of interfaces to the brain are being used now and will be used in the future to treat a variety of different nervous system disorders. And if you do something as silly as type brain-machine interfaces into Google, unfortunately what you get is something like this, which is a pretty crazy collection of images that you may not be too inspired by. But it's actually not that crazy. It's not even science fiction. It's science. It's going on now. People are trying to figure out now how are we going to develop an array of different devices to treat disorders ranging from brain injury, from degeneration that can result in phenomena such as memory loss, psychiatric disorders, and many other conditions. Now, we hope we can do that, and in fact, in some cases, such as in certain forms of Parkinsonism, the only way to treat this severely degenerated and almost lost tissue is to actually come in and do electrical stimulation. But to perform more sophisticated interactions with the nervous system requires very big advances in our capacity to interact with many cells of many cell types in a region of the circuitry of the brain. And we can't do that now. So could it be that our research into the retina and doing the same kind of thing in the retina will be helpful for this? Well, we think so, and we hope so. And the reason is that although the retina is somewhat physically separate from the rest of the brain, it's actually very similar in its fundamental organization. Many different cell types organized that have different morphology, different lamination of their processes, connecting up specifically to other cell types and projecting information to a variety of different central targets in the brain. So the problems that we need to solve in terms of interfacing to the brain and the multiple distinct cell types, those problems all appear in the retina, and we can tackle them now. So we think that this kind of development hopefully will have impact on a larger collection of brain interfaces of the future. It may seem spooky to think about all these brain interfaces and the capacity to control and manipulate and augment even our capacities, but it's clear that that future is coming. And I hope that the work on the retina will allow us to unfold that future more effectively. Thank you.